a very brief introduction because everybody knows the next speaker. But anyway, so Kiran has obtained his PhD at MIT some time ago, and is now a professor at the University of California, San Diego. So he did a lot of things related to p-adic numbers, including some well-known algorithm for computing cardinalities on some Jacobians. That's it.
I apologize, Francois, I've lost your audio.
Oh, okay, but you know everything I said.
That might be my fault. One moment.
Yeah, so please proceed. Hello, hello? Can you hear me?
Kiran, we can hear you well.
Sorry, you hear me?
Yeah, I hear you, and I heard Kiran as well.
So, Kiran, did you? Apparently not.
Maybe somebody describe it.
Can you hear us, Kiran? Or seems to
he has lost our audio. It will take him a couple of seconds to fix it.
Okay, it's I have the audio back.
Okay.
Yeah, so I don't know what happened. I've never seen that before. Just the audio completely cut out for about a minute.
So you may share your screen again.
Yes, I will share my screen again as soon as Zoom is acting up on this device. Well, I have a backup plan in case I need to switch devices. I have a second device connected, but let me see if I can get this going.
Because we can see you and hear you.
Okay, so I just restarted my screen share. And give it a moment. Okay.
Yeah, it's okay for me.
So, all right. So I assume there was some sort of introduction during the part that I couldn't hear.
Yes. Yes.
Can I go ahead and proceed?
Yes, please.
All right. Thank you. So let me start by thanking the organizers for the invitation to speak and for putting this workshop together. And also for scheduling this talk at the end, because this gives me a nice opportunity to refer back to some of the previous talks. Although I wasn't able to watch all of them because of the timing, but at least based on the abstract, I can say that I'll definitely make some contact with some of the topics that came up earlier. Let's see, I should mention that these slides are posted on my website. I can also provide them to the organizers afterwards. I should give a shout out to Deeptajit Roy. A lot of these discussions were originally with him that sort of led to formulating some of these questions. And finally, I should acknowledge that my campus sits on the unceded ancestral land of the Kumeyaay Nation, who have a website with more information about their story. Right. So I'm going to divide this talk into three parts. I'm going to sort of frame three different general questions that are all about computation of objects that are of interest in number theory, and in all of which potentially there's some room for quantum algorithms to improve upon classical algorithms. In some cases, the room for improvement is potentially speculative, but I thought it was worth formulating the question. So the first of these is going to be about zeta functions over finite fields. This is probably why I was invited to give this talk in the first place. So to recall, if you have an algebraic variety of some dimension d over a finite field, which I'll call FQ, Q will be the cardinality. So you can associate it to a Hasse-Weil zeta function, which is this power series that's defined in terms of the number of FQ to the n rational points on X for all positive integers n. So it's in some sense a generating function for the number of FQ points, the number of FQ squared points, and so on. Now you put it in this slightly different form because this makes it more parallel to L functions that occur maybe in later parts of this talk, like the Riemann zeta function. In particular, if you substitute t equals q to the minus s, you get something that has an Euler product expansion indexed by closed points of this scheme, which looks very much like the Euler product of the Riemann zeta function over primes, or the Dedekind zeta function over prime ideals of a number field. So this is a natural analog. And we know lots of things about this. So the Weil conjectures were formulated in the middle of the 20th century and resolved sometime later, and they give us a lot of information about this. So this is always a power series with integer coefficients. That follows from what I said about the Euler product reformulation of this definition. More seriously, it represents a rational function in T. So there's some finite amount of information that's captured by this infinite sequence. The poles and zeros of this function in the complex numbers are all on specific circles. They all have absolute values, some power of q to the 1/2. And if x is smooth proper, say if it's smooth projective, then you have a functional equation that relates involving t going to q to the minus d times t inverse. This will be visible in some examples. So let me throw some examples on the next slide to remind you / show you what's going on here. So the most basic example of this is projective space. This is an excellent exercise if you've not worked with this definition before. The zeta function of projective space consists of the numerator 1 and the denominator consisting of 1 minus t, 1 minus qt, ... 1 minus q to the nt. For example, you can derive this from the fact that projective n space is the disjoint union of affine n space and projective n minus 1 space. It's very easy to compute the zeta function of affine n space because the number of points over any field fq to the k is just q to the nk, and then you induct. So that gives you this formula. This also, of course, has some interpretation in terms of cohomology of projective space, whatever that means. We'll come back to that a little bit later. Another example, the sort of first interesting example that was considered, if x is an elliptic curve, then you have a formula that has 1 minus t and 1 minus qt on the denominator, independent of the elliptic curve. In the numerator, you have something that depends on the curve in a specific way. The middle coefficient a is essentially determined by the number of fq points. This follows from the definition. Well, once you know the rest of the formula, this follows from the definition. And of course, a is limited by the fact that the roots of the numerator have to have absolute value q to the minus 1/2. That translates into this bound, which was originally proved by Hasse. So this is an important example in cryptography, of course. Elliptic curves over large finite fields are a basic building block of modern cryptography. You might also consider higher genus curves, which to some extent also show up in cryptography, but I won't be focusing much on cryptographic applications. But just to mention, for if x is a curve of genus G, so the previous example was the case G equals 1, you get something similar. You get a numerator of degree 2 times G with a symmetry across the middle. So the coefficients at the end are obtained by reflecting the coefficients from the beginning and then multiplying by appropriate powers of q. And again, the numbers here are constrained by the condition that the numerator has all of its complex roots having absolute value q to the minus 1/2. So in particular, there are only finitely many possibilities given q and g for each of these coefficients a1 through ag. Once you know the first half, you get the rest by reflection. And so it is a finite problem to identify these. And in particular, since you know these are integers of a bounded size, one way you could potentially bound them is using the Chinese remainder theorem if you can control them modulo some suitably large modulus. That idea will show up crucially a bit later. So a warning. So the basic problem that I want to formulate is in this section is computing the zeta function from a description of x. Now, when you ask a question like this, you have to be careful about what constitutes a description, because certain descriptions will lead to intractable problems. So for example, if you're allowed to specify X in terms of equations in an uncontrolled number of variables, and the length of the complexity of the problem is dictated by the length of the list of equations, then you get an NP-complete problem, because you can formulate something like 3-sat as a special case of this problem, right? 3-sat can be formulated as the question of writing down a certain affine algebraic variety over F2 and asking whether or not it has 0 F2 points. The zeta function certainly contains that information, because it has the information of the number of points over all extensions of F2. And so this would give you an NP-complete problem. And the reason is that the dimension of the variety is somehow part of the input. So for this reason, I will generally take the dimension to be fixed. This tends to avoid this kind of reduction. And it still leaves a very interesting problem, because I can still vary the cardinality of the base field, and of course X itself, but I can vary X within a class, and I parameterize based on the arithmetic complexity, roughly speaking, the number of coefficients in some polynomial representation that it would take to specify X, but we agree that it's a dense representation and not some kind of clever sparse representation. For instance, if I require X to be an affine hypersurface, then I can use the degree of the defining polynomial. And of course, because D is fixed, there's a polynomial relationship between the degree of the defining polynomial and the number of coefficients. In the case where D equals 1, most often we're talking about smooth projective curves. And then we could use the degree of a defining polynomial for some singular plane model, but it's more natural to talk about the genus. Those are polynomially equivalent. So it's not a serious discrepancy, but it makes it a little bit confusing to pass from the curve case to the general case. So I will sometimes formulate things in terms of degree, even in the case of curves, whereas really what you find in the literature is complexity based on the genus. Okay. So yeah, so now we have a general problem to go from a variety X described in some explicit way and with bounded dimension to its zeta function. So here are some classical results that we have on this problem. To make these easier to formulate, I'm going to just assume that X is a hypersurface in projective space, in affine space, actually. So it's defined by a single polynomial equation. This captures all the real difficulty of the problem, because you can write any algebraic variety as a disjoint union of, or maybe with adding and subtracting of affine hypersurfaces, a polynomial number of them, and the dimension doesn't increase. So we're not really losing anything by just talking about affine hypersurfaces. And just to say, I'm going to assume everything is, all my classical algorithms are randomized. There are some very interesting questions about de-randomization, for example, when it comes to Schoof-Pila, but let me not talk about that. Okay, so the gist of this slide is that in two different directions, we have good classical algorithms, namely, so for example, in this theorem of Lauder and Wan, if you fix P, the characteristic of the finite field, but you're allowed to vary the variety, and you're also allowed to vary the extension degree over FP, but you have to fix the characteristic. Then you get a polynomial time algorithm.
So, Kiran?
Yes, go ahead.
I gather you mean randomized, but otherwise unconditional.
Yeah. So I want it to be randomized, but I want the Yeah, so I guess I could say this is, what do we call this? Las Vegas, where the runtime maybe is allowed
No,
to.
no, I didn't mean, yeah,
I just
no,
mean,
Las Vegas is another thing. That's called ZPP also, where the answer is known to be correct. You just the only uncertainty is whether it's fast.
yeah, I think that's actually what I want here. I think these.
No, but my question was something else, which is
Okay.
which is regardless of whether you can whether which style of randomized computation it is, whether these results, these theorems don't depend on any standard super hard conjectures.
Oh yeah, these are not conditional on any deep mathematical results. I will come. There will some results later will depend on things like BSD or forms of GRH. None of these is conditional in that way.
Do you get, if you're allowed to assume big ticket conjectures, then
for this question, I don't. Yes, so some de-randomization. So right, right. The basic de-randomization problem that comes up is, de-randomizing, general polynomial factorization over finite fields. So in particular, taking square roots or something like that. And that is de-randomized under GRH by theorem of Burgess, is it? On the smallest, the smallest quadratic non-residue.
Okay,
So-
cool, interesting. So in other words, it's all ZPP, which is the mildest form of random.
Yeah, so these are randomized in a very
moreover,
weak sense.
Deterministic polynomial time, assuming GRH.
Yeah, I think the only one that the first and third of these, I think, don't even have that. I think they really are deterministic. I would have to double check that. The Schoof-Pila,
anyway,
I think I might need.
Yeah.
It's possible I'm misremembering, and I'm just but in my head, Schoof-Pila requires some polynomial factorization. But maybe somebody can correct me if I'm.
Despite my
No,
question, I'm
no,
actually more interested in the rest of your talk. So I'll.
Yeah.
Thank you.
So Schoof-Pila is deterministic. If you use isogenies, then it is probabilistic.
That's true. So if I just want polynomial time, it's deterministic. If you want to improve the polynomial, you can do that in a non-deterministic way. That's right. Thank you. Okay, so let me go back to actually saying what's on these slides, now that we've had the slide discussion already. So Lauder and Wan show that if you fix P, the characteristic of the finite field, then you have a polynomial time algorithm to compute zeta functions in the rest of varying the rest of the input data. In the other direction, you can add, and there's a similarly for David Harvey. Well, let me do Schoof-Pila next. So Schoof-Pila is kind of in the opposite direction. It's specifically for curves, but it is a situation where you have a curve of a given genus, and you want to vary the base field. And Schoof-Pila gives you a polynomial time algorithm for computing zeta functions in that direction. So you vary the base field in this case. In the second case, in the first case, you fix at least the characteristic of the base field, and you vary the variety. But you're allowed to scale with the degree. The Schoof-Pila has at least an exponential complexity in the degree. So, and I want to mention that David Harvey has a theorem that says that if he has various results, but I've quoted one of them. If you fix X, so you don't get to vary X at all, but if you sort of specify X in advance, and now you want to vary you sort of essentially you fix X defined over the rational numbers, and then you reduce modulo various primes. You can compute this zeta function from X in time polynomial in log Q, but you have to do some large amount of pre-computation based on X. So this is kind of a sample of different results in this space. And none of these is what I actually want, which is I want a polynomial time algorithm for dimension fixed, but I'm allowed to vary both the base field and the variety in a polynomial way. So, however, for d equals 1, it turns out, so I proved some years ago that in dimension 1, there is a quantum algorithm that achieves this goal. So for curves, there is a quantum algorithm to compute the zeta function in time polynomial in both the complexity of the curve and the log of the cardinality of the base field. So really in the length of the input data in a typical representation. And the point is that in this case, we can interpret the zeta function in terms of orders of abelian groups, that being essentially the one thing we know how to do with a quantum algorithm more efficiently than a classical algorithm. And the abelian groups in question are the groups of fq to the n rational points for varying values of n of the Jacobian variety. So this is an abelian variety of dimension g. So it's some projective variety that is maybe not so easy to write down in terms of equations, but you can compute with it in terms of divisor classes. So you can do arithmetic on the Jacobian decently well. And its order is related to the numerator of the zeta function of the curve. Remember, I showed you earlier the zeta function has this form with this denominator that's fixed and a numerator that's a polynomial of degree 2g. And the order of the Jacobian over fq is just the evaluation p of 1, and over fq to the n, it's this, so to speak, base change of p. It's something you can read off from p. So if you knew p, you could compute these orders. But of course, in the world of quantum algorithms, what you can do is go in the opposite direction. You actually have as many of these orders as you want by Shor. Shor's algorithm will give you these for polynomially many values of n. You need about 2g of them in my paper. You can probably do better than that, but at least it's going to be some linear multiple of the genus. Anyway, it's polynomial. So you have that many group orders, and then you can do some slightly fiddly calculation to recover the roots of this polynomial p from these orders. Essentially, what you do is you take logarithms of these things and you do some, you set up some matrix inversion that approximately computes these roots. And then you use the fact that the coefficients of this polynomial are integers of bounded size. So once you compute them numerically, well, first of all, you don't even need them to be bounded size. You know they're integers, so once you compute them to within 0.5, you've got them on the nose. So yeah, so this shows that at least to the state of our current knowledge, quantum algorithms outperform classical algorithms on this problem when d equals 1. So the main thing I want to ask in this part of the talk is there a similar algorithm for d greater than 1? Now for that, I almost certainly will have to use some more advanced mathematical knowledge about the zeta function, namely the fact that this is how we prove theorems about the zeta function in general, is that we have the Lefschetz-Trace formula, which interprets the zeta function as some alternating product of polynomials, which are the reversed characteristic polynomials of some linear operators acting on some finite dimensional vector spaces. And these are written to be, these h upper I of x are notated so that you think of them as cohomology, some kind of not a linearization of the nonlinear geometry of x in finite dimensional vector space that captures some interesting information about this highly nonlinear object. And the f, the linear operator on that, is supposed to capture the action of Frobenius. Frobenius meaning if you have something defined over fq, then any point on that over some extension field, if you raise each coordinate to the q power, you get another solution of the same set of equations. So that by some cohomological magic, that's supposed to give you some linear endomorphism of this vector space. And so if you can actually not only define such a thing, but compute with it, then you potentially can write down an algorithm to compute zeta functions efficiently. And there are two standard approaches for defining such spaces. One is Étale cohomology, and Étale, you need to be working over some field of characteristic 0 so that you actually, otherwise you only get information about the zeta function reduced modulo some prime. Now with Étale cohomology, in principle, you define it over QL, where L is some prime not equal to P. But in practice, you actually work with it with mod L coefficients, but you don't use one L, you use a bunch of small values of L. And as I said earlier, if you can pin down the zeta function modulo a bunch of small primes, then the Chinese remainder theorem isolates a unique value for you. So Étale cohomology, for the sake of computation, you typically just work with mod L coefficients, where L is some prime that's, say, logarithmic compared to P, or logarithmic compared to the size of stuff in the problem. So it's logarithmic compared to Q, maybe I should say. So the other approach that's typically used is various constructions related to crystalline cohomology. You may have seen some of my work on this in this direction. In this case, what you get for K is K will be some finite extension of QP, where P is the characteristic of the finite field. So here you have to worry because this P could potentially be large. So you can't do things that are polynomial in P and hope to get polynomial time algorithms, because the size of P is exponential in the length of P, which is what we care about. Right, so let me first talk about the crystalline cohomology groups, because basically to get them out of the way, they are quite useful for practical computations. There are various ways to define them. The traditional definition in terms of the crystalline site is not super computable, but there are other models of p-adic cohomology that are much more computable, like Monsky-Washington cohomology. So this is used in various packages. Pari, Sage, and Magma all have implementations of various forms of Monsky-Washington cohomology for the zeta functions of things like hyperelliptic curves. These are quite practical for small base fields or for large base fields of small characteristic. But as far as anyone knows, they always involve polynomial dependence on the characteristic of the base field.
So,
Greg, go ahead.
Kiran, so just a theoretical point about your previous slide. You don't have to go back to it.
Oh, okay. Well,
do you mean to say? Do you mean to say that Étale and crystalline cohomology yield two different proofs of the Weil conjectures?
That is correct. They are different in that they use different foundations. They are quite similar in that once you've set up the two theories, the proofs are run quite parallel to each other. So they basically, they give you two, so roughly speaking, they give you two implementations of the same proof.
Okay, and the two known implementations.
Yeah, there are two known implementations. It is entirely conceivable there's some other idea that would give you a quite different implementation. But you know, the question of providing a new implementation has been around for more than half a century, and we haven't seen one. So this is what we're stuck with for now.
Stuck with it's good stuff.
No, it's good. But I'm about to tell you. I'm about to tell you why crystalline cohomology is tricky and Étale cohomology is, you know, also tricky, but maybe better for this problem.
Okay.
Yeah. So that conveniently gave me a chance to wait for a plane to fly by. So crystalline cohomology, as far as anyone knows, every computation that involves crystalline cohomology involves polynomial dependence on the characteristic of the base field. You can sort of cheat and amortize over primes if you're doing many of them at once, which is actually the case of interest when you're working with L functions of varieties over number fields. in that case, you actually start with a single variety over a number field, and you have to do many of these problems amortized over multiple primes, and then you can achieve average polynomial time. But if you have a single, say, cryptographic size prime, these techniques are of no help. You can sort of conceptualize the difficulty here by thinking about the following problem, which in some sense all computations involving crystalline cohomology eventually reduce to. You have some power series over Q that you specify by writing down an ordinary differential equation, say a fixed ordinary differential equation, and fixed initial coefficients. So you specify this power series this way, and let's assume that it's set up so that for most primes, the pth coefficient is p-adically integral. So then, the problem is to compute the pth coefficient modulo p in time polynomial in log p. So faster than doing the computation over z mod p, all the way out to p steps, because that clearly isn't polynomial in p. Now, what Harvey observed some time ago, based on this is, I think, based on, well, this idea goes back to the Chudnovskys, that you can kind of baby step, giant step one of these linear. This is right. The Frobenius method gives you some recurrence, not with non-constant, but mildly non-constant coefficients for the coefficients of the power series, and you can, so to speak, baby step, giant step that recurrence to get the dependence from linear in P down to square root of P. But as far as anyone knows, we can't do better than square root. So that breaking that square root barrier for some problem like this would be a huge theoretical advance, classically or quantum. But I don't know how to break that barrier. So instead, I want to think about Étale cohomology groups where so Schoof-Pila, roughly speaking, is using Étale cohomology with FL coefficients. So what Schoof-Pila does is you compute in the torsion, the L torsion of the Jacobian variety. And that gives you a computable model for the first Étale cohomology of a curve. And that gives you a polynomial time algorithm when you fix the dimension. The problem is you end up having to do linear algebra in a vector space, in a, so to speak, black box vector space. And when you do that classically, the complexity of that involves the cardinality of the vector space. But quantumly, doing linear, like finding the characteristic polynomial Frobenius of a hidden linear transformation is effectively it's an abelian hidden subgroup problem, right? You kind of write down a homomorphism, a computable homomorphism into your black box vector space, and you're just asking for the kernel. So if I write down, if I had a mechanism to write down Étale cohomology groups in some computable way, then that would give me some polynomial time algorithm. Well, I sort of already have that. There's a theorem of Modular and Orgogozo that proves that Étale cohomology is computable, but you still need a complexity analysis because you need to know that you need to know it's polynomial time computable. So if you can improve the theorem of Modular and Orgogozo to get polynomial time computability, then you would get a quantum polynomial time algorithm for zeta functions. So this is the essentially open problem in this section of the talk, is to give a polynomial time improvement of the theorem of Modular and Orgogozo. I haven't looked at this paper very carefully. It's possible it's not that hard to do this, but it took them some work to just prove computability at all. So it might not be so easy. Greg, you have another question?
Yeah, I hope I'm not wrecking the timing of your talk.
No worries. No, this bit is supposed to be the longest section, so the other ones are short.
Okay, but the third paragraph brings me to the crucial point that you may have been busy, but I sent you email, and actually my talk was about
yes.
Shor-Kataev. Is this what Shor-Kataev actually does, where the hidden subgroup has finite index or equivalently maximum?
Yeah, because we're talking about finite dimensional FL vector spaces. Right, I have a finite dimensional FL vector space that's computable, and I have a linear transformation of it that's computable. So, right, what I do is, the way I write down a Shor-Kataev is I pick some element of this guy, and then I write down a homomorphism, from the free vector space on enough generators that sort of maps each generator to the image of this guy in my target group under the appropriate power of Frobenius. And then I ask for the kernel of that map. And that computes the minimal polynomial. Well, that computes some factor of the minimal polynomial of f, but it computes something useful. But everything is finite in this.
No.
Yeah?
No. This is something, first of all, I'm a little bit lost by your answer, and maybe we should discuss later. But the distinction I have in mind is let me put it this way. Even though I didn't quite follow your answer, you have a hiding function from your group, and it has hidden periodicity.
Yeah.
Is the target of the hiding function a finite set?
Yes.
Okay. Then it's Shor-Kataev. That's right.
Yeah, because you have representations of elements of the Étale cohomology group. That's the target, right? The codomain of the target function is the sort of representation of elements in Étale cohomology.
Well, I didn't, in this L-adic situation, you eventually get.
Well, it's as mod L, not really L-adic.
Oh. Okay.
I'm doing everything modulo. I'm doing everything with mod L coefficients.
Okay, so the target is made from linear algebra mod a finite field.
That's
so
right.
So that makes the target a finite set. Okay, thank you.
That's the point. Yeah, great. All right. So fortunately, that was the end of this section. So let me pause for a moment to see if there are any more questions about the first section before I move to the second. All right. So the second one, I'm going to go through this more quickly because I think there's actually some overlap with Kumar's talk, which I wasn't able to attend, but I'm looking forward to watching the recording. So this section is about computing things associated to modular forms. So as a reminder, a modular form of weight K is some holomorphic function on the upper half plane that satisfies some gross condition plus a functional equation in terms of matrices, some invertible matrices over the integers. So you typically impose some congruence condition that specifies a level. And okay, if you haven't seen this definition before, this is pretty opaque, but there are lots of interesting examples in number theory. And generally, the way you deal with these things is you fix a weight, you fix a level, and then you're talking about a finite dimensional vector space of these things. So computing with them is a computationally feasible task. And moreover, these things will have a Fourier expansion because you always have the translation by z goes to z plus n, because 1, 0, 1 n 0 1 is always congruent to the identity mod n. So you always have a Fourier expansion in some fractional powers of e to the 2 pi I z. Many cases of interest, you actually have integral powers of e to the 2 pi I z, but at this level of generality, I have to allow the fractions. So there's a very nice theorem that generalizes Schoof-Pila in some sense, or it's a variant of Schoof-Pila. It's due to Couvain and the late Bas Edixhoven. If you take a fixed modular form of weight at least 2 with coefficients in some number field, this coefficients in some number field is not a serious restriction because the whole vector space can be defined over some number field. So really, this theorem is really about the eigenvectors for Hecke operators, but I can state it this way. So there exists a classical algorithm which, given a factored positive integer n, will compute the nth Fourier coefficient in time polynomial in log n. So of course, in the world of quantum algorithms, the n, you don't have to give the n as factored because you can factor it. But the point is that other than factoring, this is a classical algorithm. And I didn't check. I believe this is actually as deterministic as Schoof-Pila. Maybe Francois can correct me if I'm wrong, but I believe this is completely deterministic. And indeed, the proof is very similar to Schoof-Pila. You compute some kind of what's called a Mordell-Weil representation that tells you the coefficients of f modulo a prime L. And well, if you have enough of those, you have some bound on the Fourier coefficient, which is polynomial n, that then you can just put everything together by the Chinese remainder theorem. So this is some variant. Let's see. I see Greg and Kumar have hands up. Greg, is your hand still up from before, or is this a new question?
It is a new question, but I want Kumar to go.
Okay, Kumar first.
I was just wondering whether I thought they had to assume the Riemann hypothesis. Is that not true?
Oh, they might. Yes. So this might be a case where, yeah. Let's go ahead and assume. I don't remember what GRH you need. Maybe is it just for quadratics or number fields, or do you have to for the modular form as well?
Not for the modular form, for Dedekind L functions.
Oh, for Dedekind L functions. Okay, so this is, yeah, I should put an asterisk here, sort of under some form of GRH. So it's deterministic, but not unconditional. Greg, did that answer your question, or do you still have a question?
What is the data type for this of how is the modular form conveyed to the computer in the
well, the way I formulated this is that I sort of cheated and formulated this where the algorithm is allowed to depend on f. But if you actually you can I don't remember to what extent you can uniformize this over f, but in principle, the way you would specify f is you would specify a weight and a level, and then some initial number of Fourier coefficients. So the weight and the level would would give you a finite dimensional vector space, and there's an explicit bound by Sturm that tells you exactly how many coefficients you need to specify the modular form.
Okay, so in that sort of way, algebraic modular forms defined over a number of fields have a finite description that you then
yes, the catch is that I didn't check to see to what extent the statement of the theorem is uniform as you vary the modular form. So I didn't want to state more than I knew.
Okay, anyway, that answers my question. Thank you.
So it's an interesting question, which might be answered by just reading their book more carefully. But it is an interesting question, how uniformly can you do this? So that's a question. But I want to mention a couple of other questions that I know less about. One is there are modular forms of weight 1 as well, which are not directly related to Galois representations in the same way. I suspect I didn't check either of these details, but you should be able to improve the previous theorem to cover weight 1 by using congruences between modular forms. So this is how we know most things about modular forms of weight 1 is that you identify congruences modulo specific primes between weight 1 modular forms and higher weight modular forms. The catch is the weight will depend on the prime. So you actually do need to figure out the uniformity that I was just alluding to in order to make this work. Or coefficients of weight 1 modular forms can be interpreted in terms of orders of class groups of quadratic fields. So if you go back to Mike Jacobson's talk, he told us about quantum algorithms for this problem. So this again maybe can be used to get a weight 1 version of the Couvin-Edixoven theorem. I didn't check either of these. These are both. You should think of these as open problems, but maybe not so difficult. Maybe I'm wrong though. The problem I wanted to focus on, because I have really no idea how to do this, is modular forms of half integral weight. These come up as theta series of quadratic forms. For example, modular forms of weight 3/2 come up as theta series of ternary quadratic forms, which are kind of an interesting boundary case in number theory. These don't have a direct interpretation in terms of Galois representations. So it would be an interesting problem to give some good quantum algorithm for expressing these. If you try to write these in terms of class numbers, you get sort of long sums of class numbers, at least if you do this in a naive way. So there's a question of whether you can write these things as short sums of class numbers. And one motivation for doing this is that, okay, for this you have to assume at least BSD. You don't have to assume modularity of the curves because that's a theorem, but you have to assume the Burt-Swinnerton-Dyer conjecture. Right, there's an old problem of determining whether or not a positive integer is what was classically called a congruent number, i.e. the area of a right triangle with rational side lengths. So there's an old theorem of Tunnel that reduces this problem to computing some Fourier coefficient of some half integral weight modular form. But it's the coefficient, the index of the coefficient is a linear function of n. So you need so we don't know a classical algorithm for this. And we don't know a quantum algorithm either, but I have some hope that maybe you can do better with a quantum algorithm. So here's another interesting problem. I think this is the last, oh no, I have one more thing on here. I'll just mention this briefly because this probably there was more about this in Kumar's talk than I have to plan to say. You can also think about the L function associated to a modular form. This is the Dirichlet series, and there's a lot of interest in computing values of this. For instance, if you want to try to verify the Riemann hypothesis for a particular L function, this goes back to Turing. As far as I understand, this was Turing's motivation for getting interested in computational, machine computation, and then he got kind of sidetracked with that. I think Andy Booker's PhD thesis sort of narrates some of this backstory in some detail. He and David Platt have done a lot of work on, for example, computing zeros of the Riemann zeta function. This computation, the key thing in this computation is a discrete Fourier transform. So I'm just going to throw out as a poorly formed question, do quantum algorithms actually give you any improvement for this problem? I have no idea. There's already been, you can already do computations of zeros of the Riemann zeta function quite far. I mean, Platt has trillions of them. But maybe quantum algorithms give you better dependence on parameters. For instance, if you consider Dedekind L functions and you vary the conductor, maybe you get better dependence on the conductor. Again, I'm probably not the expert on this question, so I'll maybe just leave it at that. Okay, so I have about 10 minutes. So the last thing I want to do is, this is only a couple of slides. So I want to mention a couple of problems related to elliptic curves. So this starts with the Mordell-Weil theorem, says that if you have an elliptic curve over a number field, then the rational points, which have a group structure from classical algebraic geometry, they form a finitely generated abelian group. So in other words, you can describe all of the solutions in terms of some finite generating set. Now, this already runs into a very serious problem, is that unconditionally, there is no known algorithm to compute this group or even to find its rank. If you assume BSD, though, you can do a day-night search where by day, you look for rational points on the elliptic curve. And by night, you numerically compute derivatives of the L function, which will give you an upper bound. As soon as you can prove that one of these L functions has a non-vanishing derivative of some order, you get an upper bound. I should say, I'm also assuming the modularity of the elliptic curve in question. So over Q, this is an unconditional theorem. Over some other fields, totally real fields, CM fields. But in general, the modularity of a general elliptic curve is also a conjecture. So I should have assumed that as well, because I need that to make this upper bound rigorous. I mean, even assuming BSD. So that makes it a little bit hard to ask questions, but if you assume that the rank is fixed, say the rank is 1, you can then ask, can I compute a generator of this group in time polynomial in the bit complexity of a description of E. So that's going to involve the discriminant of the number field and the logarithm on the log heights of the coefficients of E. And, you know, in some sense, this question has an information theoretic negative answer because the generator is too big to write down. But, you know, we've solved this problem before as a community. You can solve this problem if you can give a compact representation of the generator. For example, if you have small points defined over a small extension field, and you can write down some linear combination of them with large coefficients that gives you this generator, then that would be a description of the point that you could potentially compute efficiently. And of course, this is meant to be analogous to something we know from, you know, an analogous problem. If you have a real quadratic number field, the group of units is generated by is rank 1, generated by a fundamental unit. This is a solution. This fundamental unit solves an equation that is studied by various people and is attributed to none of them typically. But nonetheless, it's an equation that we know a lot about. And in particular, we know that the x and the y might be large. X and y might have exponentially many digits. So we can't write them down directly, but there are compact representations. You can express the fundamental unit as a product of not necessarily units, but algebraic integers in your number field, which are small but raised to large powers. And then so Sean came up with a quantum algorithm to compute this fundamental unit, which was then extended to arbitrary number fields. So in this situation, so for the problem of computing units of number fields, this information theoretic problem is an issue, but you can sidestep it. And so the question I want to ask here is there a way to sidestep the bit complexity of the generator of an elliptic curve when you have rank 1 using some sort of compact representations? For example, when E has analytic rank 1 over Q, analytic rank 1 meaning the L function vanishes to order 1, then it's a theorem by Gross-Zagier plus Kolyvagin that BSD holds in this case, at least in the rank aspect. So, and you can generate points of E of Q by taking traces of CM points on modular Jacobians. This is the method of Heegner points. This is in the spirit of a compact representation, except the dimension of the Jacobian is exponentially large based on the conductor, and the degrees of the CM points are also exponentially large. So this isn't actually a solution to the problem, but it does at least suggest a point of view that might lead to compact generators if you could come up with some more efficient way to generate points on elliptic curves over Q. So, so this is at least a hint that there might be something to be done in this direction. And I'll just end with a provocative but very speculative slide. Potentially there's some other way to represent the group EK that might yield a compact representation. And the motivation for asking about other representations is that so Kato has a proof of BSD in the case where E is of analytic rank 0. So this case is not so interesting from the point of view of computing the rational points because they're just torsion points, and there are good algorithms to find the torsion points. There's a theorem of Mazur that bounds the number of them, and you can find them by reduction to finite fields relatively easily. But the proof that Kato gives of BSD in this case is super interesting. It uses certain elements in algebraic K theory. So the provocative question, of which I have no idea how to proceed, is, can you do something similar when the analytic rank is 1? And if you can, does that lead to better compact representations of rational points on elliptic curves than the Heegner point method does? And I honestly have no idea. So I don't even claim that this is like a reasonable thing to be thinking about, but it's a provocative question. And I think it's a good place to end this talk and this conference with. So let me wrap there. And one more time, thanks the organizers for the invitation.
Okay, thank you for this talk. So we already had a lot of questions. Are there more?
Could I ask a question?
Yes, I see Ehsan, you have a question. And then Kumar. I saw Ehsan first.
Yeah, can you hear me?
Yes, I can hear you.
Yeah, thanks.
Oh, by the way,
I
are we supposed, hold on, before we continue though, are we supposed to turn off the recording before we start having questions?